Guess what? We've got even more to say about Lewis structures. So we have already drawn the Lewis structure of nitrate. Let's talk about the Lewis structure of SO3 2 minus, sulfite. Sulfate, remember, is SO4 2 minus, sulfite, SO3 2 minus. So we've got 6 plus 6 times 3, that makes 18, plus 24, plus 2 more is 26 electrons in sulfite. So put the least electronegative atom in the center, that's sulfur. Put oxygens all around the outside. Fill up everybody's octets. Oxygen needs 6 more to have an octet. Oxygen needs 6 more to have an octet. Oxygen needs 6 more to have an octet. Sulfur needs 2 more to have an octet. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Woo woo! 26 electrons have been used. We had 26, we used 26. Whoop whoop! But before we celebrate too much, let's talk about the formal charges. What? Yep, formal charges are needed on this thing. One signal how I know I need to add formal charges is if the atoms are making more or less bonds than they like to make. So oxygen is in group 6. He needs 2 electrons to make 8. So that means he likes to make 2 bonds. He's only making 1. He's only making 1. He's only making 1. Sulfur likes to make 2 as well, but he's making more than 2. So if we go through and assign formal charges here, remember the formal charge formula is number of valence electrons. So for oxygen, that's 6, minus the number of lone pair electrons plus 1/2 the number of bonding electrons. So this is a -1. And all 3 oxygens have the exact same formula because they're all making 1 bond. And then sulfur is in group 6. He's got 2 lone electrons plus 2, 4, 6 bonding electrons. 1/2 of 6 is 3. So it's a +1. So this Lewis structure has formal negative on all the oxygens plus a positive on the sulfur. We're going to revisit this, but we're going to move on for right now. What if I draw ClO2 minus? So chlorite has 7 plus 12, that's 19 plus 1 more, 20 electrons in chlorite. Put the least electronegative atom in the center, that's chlorine. We'll put oxygen on either side. Fill up the octets of everybody. Oxygen needs 6 more to have full octet. Oxygen needs 6 more to have full octet. Chlorine needs 4 more to have full octet. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Whoop, 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 whoop. But wait, before we celebrate too much, we need to add formal charges to this thing. Oxygen is in group 6, so he's got 6 valence electrons, minus he's got 6 lone pair electrons here, plus 1/2 the number of bonding, that's 1. He's a negative. Oxygen is a -1. Both of these oxygens are making 1 bond, so they are a -1. Chlorine is in group 7, so he's got 7 valence electrons, plus 4 lone pair electrons, plus 1/2 times 4 bonding electrons. 1/2 times 4 is 2. That gives me a plus. Chlorine is a +1 in this Lewis structure. Okay, we're going to revisit it. Hold on. The octet rule only applies to carbon, nitrogen, oxygen, fluorine. What? Yeah, hold on. We're going to say more. Sometimes you can't get everyone to have an octet because you have an odd number of electrons. And when you have an odd number of electrons, you're not going to be able to pair up everyone to have 8 around everything. An example of this is NO. Nitrogen has 5 and oxygen has 6. That gives me 11 electrons. This is not an NO minus. This is an NO, period. So if I try to draw the Lewis structure of NO, I'm going to have N bonded to O. That's only 2 electrons, so let's go ahead and make it a double. 2, 4 electrons. Fill up the octet of oxygen. 2, 4, 6, 8, 9, 10, 11. What? Yep. We have an unpaired electron on that nitrogen. An unpaired electron is called a radical. This molecule is called a radical molecule. The radical is specifically on nitrogen. Ugh. How do I know that the radical needs to be on nitrogen more than oxygen? It's all about electronegativity. This nitrogen does not have a complete octet, but this oxygen does. If I get the choice between one of these having to be without a full octet, the least electronegative atom is more okay with having the not octet. That's a really weird way to say that. The least electronegative atom is more reasonable. It's less selfish, so it's more reasonable for the least electronegative atom to have the not octet. Yeah, rewind that and watch it a few more times and maybe it'll make sense, or maybe it won't. So the octet rule applies to these. If you have an odd number of electrons, you're going to have at least one little radical dot of unpaired. The octet rule applies to the small atoms in the second period. That's carbon, nitrogen, oxygen, fluorine. If you're in the third period, that's 3p as in SPD kind of thing. If you're in the third period, that means your valence shell is n equals 3. You remember this, right? Valence shell is n equals 3, and the third shell of electrons can officially hold 18 electrons. So elements in the third period can have more than 8 in their valence shell. And that's called the expanded octet. An example of something that has an expanded octet is IF5. That's really 7 times 6 because fluorine has 7 valence electrons and iodine also has 7 valence electrons. So that gets me to 42 total electrons available. That's a ton of electrons. So I put I in the middle, least electronegative in the middle, and all the other things around the outside, around the outside, around the outside. So I goes in the middle because it's least electronegative, and all of the F's go around the I. What? How do I know that? Well, all of the F's like to make one bond. Fluorine is very electronegative, so it really doesn't want to make more than one bond, if at all possible. So we're not going to make some sort of chain with fluorines. We're going to have a central atom with all the F's around it. So once I have central atom with all the F's around it, I can already count 2, 4, 6, 8, 10 electrons around my iodine already. That's more than 8, but I is way down yonder in the 5th period, so it certainly can have more than 8 electrons in its valence shell because it's way, way down there. So if I continue on my Lewis structure, fluorine needs 6 more to have full octet, so I put 6 around all of these fluorines to fill up their octet. Fluorine cannot have more than 8. Nitrogen cannot have more than 8. Oxygen cannot have more than 8. Carbon cannot have more than 8. You got to be in the 3rd period and beyond to have more than 8 in your valence shell. Okay. 2, 4, 6, 8, 10, 12. 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. Oh, it's real hard to count sometimes. So I have used 40 electrons. I've got 2 electrons left. Where do those 2 electrons go? All of my fluorines have an octet. When you have leftover electrons, add them to the central atom. So those remaining 2 electrons actually go around the iodine. So the I has 2, 4, 6, 8, 10, 12 electrons around the I. But that is totally acceptable because I is in the 3rd period and beyond. It's in the 5th period, but it's 3rd period and beyond. So I said we would revisit our old molecules. If we go back, this molecule has a sulfur in it. And sulfur is in the 3rd period. So sulfur can officially have more than 8 electrons in its valence shell. So when you have an atom like this, it is often a good idea to try out a Lewis structure where you have more than 8 electrons in that valence shell to see if it makes for a better Lewis structure. How do you know if something's a better Lewis structure? Hold on. So if I turn this single bond into a double bond, my sulfur now has 8 electrons around it, so do all of my oxygens. But 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, I've got 2 more electrons that I didn't represent. Put them on the central atom because it can have an expanded octet. So this Lewis structure, if I go through and assign formal charges, I can say, that oxygen up top was a negative over here, and I didn't change anything about it. It's still a negative over there. So was the oxygen down there. Let me put my oxygen's charges, negative, negative. This oxygen now needs to be recounted. I demand a recount. 6 is its valence number of electrons, minus 4 plus 2. It's got 4 bonding electrons, 1/2 times. Yeah. This is now a formal charge of 0, and we don't write out a formal charge of 0. Okay. Sulfur needs to be recounted. It's in group 6. It's got 2 electrons plus 2, 4, 6, 8 bonding electrons. So 1/2 times 8 is 4. So now that sulfur has a 0 charge. So if I compare the blue structure to the purple structure, which structure is better? The blue structure is a better representation of SO3 2- sulfite because it minimizes formal charges. You're still going to have a -2 because the overall structure has to have a -2, period. But you get to cancel out 2 of these formal charges by showing sulfur having an expanded octet. So blue structure is my winner chicken dinner. This one is the good one. So, before I go far away from here, is sulfite best represented by that single blue Lewis structure or multiple resonance structures that have that double bond hopping around to those other oxygens? Hopefully you say option number 2. That double bond could be between this oxygen where we showed it, or this oxygen, or that oxygen. All 3 of those bonds have equal length and equal strength because sulfite is really best represented by 3 Lewis structures that have this similar setup. Oh boy, yep. I said we would also revisit this one because look. I have an element from period 3 as my central element, and I've got formal charges. I bet I could make some bonds between chlorine and maybe oxygen to have fewer formal charges and maybe a better Lewis structure. All I did here was took an electron pair off of oxygen and shared it between oxygen and chlorine to expand chlorine's octet. Chlorine had 8 electrons here, 2, 4, 6, 8, 10 electrons around chlorine here. 2, 4, 6, 8 around oxygen. Oxygen cannot have more than 8, ever, never. 2, 4, 6, 8. Oxygen cannot have more than 8, never, ever. But chlorine can because he's period 3 and beyond. Okay. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Yeah, we still have 20 electrons. This is a legit Lewis structure, this green one. But it's incomplete because we need formal charges. Oxygen over here didn't change, so leave him alone. But chlorine and oxygen, the other oxygen, did change. Oxygen's in group 6. Minus, he's got 4 non-bonding electrons plus 2, 1/2 of his bonding. That oxygen is now a 0 formal charge, so we don't put a formal charge next to it. Chlorine is in group 7. He's got 4 non-bonding electrons plus 6 bonding electrons, so that's 1/2 of that is 3. Chlorine is now a 0 formal charge. Should I say which one is my winner chicken dinner, blue or green? Green one is the winner chicken dinner. Because chlorine is a period 3 and beyond, chlorine can have an expanded octet. This green structure has chlorine with an expanded octet, and it minimizes the formal charges overall in your molecule. Yeah? Yeah. Is this green molecule the only proper representation of chlorites? No way. We can do resonance where the pi bond is, where the double bond is on this side or that side. Those bonds have equal lengths and equal strengths. Yeah. 2 final examples of expanded octets. Am I ruining the fun here? Yeah, expanded octets. Bromine has 7 valence electrons, so does chlorine, so that's 7 times 3 is 21 electrons up here. 21. So with an odd number of electrons, I know I'm going to have an unpaired electron here. I'm going to put Br in the center because it's least electronegative. I'm going to fill up the octets of everybody. Chlorine needs 6 more. Chlorine needs 6 more. Bromine needs 4 more. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Oh, I got 1 more electron. When I have 1 extra electron, it's unpaired and it goes on the central atom. So, do I need formal charges? Chlorine is in group 7. He's got 6 non-bonding electrons. 1 he's sharing in a bond. Nope. Chlorine's got 7. He's got 6 he's not sharing, and 1 he's sharing in a bond. Nope. Bromine's in group 7. He's got 5 plus 2 that he's sharing in electrons in bonds. Nope. This is the Lewis structure of BrCl2. It's a radical. There's an unshared electron around that bromine. I probably should draw it at a little bit different bond angle so that it's a little more obvious what's what. There's maybe a little better structure. As soon as we finish these expanded octets, the next thing we're going to talk about is the shapes of molecules and what kind of bond angles there are. Like chlorine, bromine, chlorine, what kind of bond angle does that thing take on? It takes on a certain bond angle because of all the lone pairs around that bromine. That's as much as a preview as you're getting right now, but there it is. 4 times 7 plus 6 more. I need math. If I did it right, it's 34 electrons. Least electronegative in the center. All the F's around the outside, round the outside, round the outside. Fill up the octets of everybody. And then count how many you've used. 2, 4, 6, 8, 10, 12, 14, 16, 18, 21, 18, 20, 22, 24, 26, 28, 30, 32. I've got 2 more. When I've got 2 leftovers, put them on the central atom. The central atom is sulfur. Sulfur's in period 3. He can handle an expanded octet. A better way to visualize this molecule is maybe something like this, where that lone pair as absolutely should be thought of as taking up space around that sulfur atom. Because like I said, the next thing we're moving into is the shapes of atoms around molecules. The shapes, the bond angles, the shapes of atoms. Period. Whatever. Blah, blah, blah. Be done. Goodbye.